Hi, and welcome back to this course on space vehicles and orbital dynamics. In this video, we are going to cover the last part of the first chapter of the lecture notes, which is dedicated to the two-body problem. We will begin by introducing the Lagrange coefficients, which are a different way of parameterizing the trajectory of our satellite. Next, and in the rest of the lecture, we will dedicate our attention to the problem of relating time with the position of our satellite. This is a complex problem that cannot be solved analytically in the general case, and one can resort, for example, to a series expansion. We will see that this approach works, but it's not the most recommended one, as it's only advisable for very short times from the initial data. The actual approach that is used to solve the time problem is using Kepler's equation. So the center part of this lecture will be dedicated to solving and obtaining the Kepler's equation in the three different cases, starting with the elliptic case and the hyperbolic case, and finishing with the parabolic one. Finally, and to close the lecture, we will just make a brief comment on universal variables, which is a way of covering the three different cases in a single formalism. All right, so starting with Lagrange coefficients, as we just said, they are an alternative way of providing the trajectory of your satellite. And this alternative way is more convenient for some particular problems. Let us focus on the fact that our initial condition vectors, the initial position and initial velocity, which are assumed known for determining the trajectory, in general are not collinear, okay, except in the generate cases which are not of interest, they will always have an angle between them. So the fact is that we can use these two vectors, which are not unitary and not orthogonal. We can still use them as a special vector basis of the orbital plane. Okay, but remember that this will be a non-orthonormal vector basis. That means that any vector that lies in this plane, for example, the position at any later time and the velocity at any later time, can be expressed in this vector basis. So we can define these initial position and velocity vectors in terms of our standard vector basis I and j in the orbital plane, as you can see over here. Now, this means a different way of expressing these relations is that if we have any vector with the coordinates expressed in the R0, V0 vector basis, okay, we can obtain the coordinates of this vector in the ij vector basis by pre-multiplying by this matrix. Okay, so this works as the rotation matrix between this non-orthonormal vector basis and the standard one. So if we invert these relations, and basically we can do it over here, perhaps it's easier, and we solve for I and j in terms of R0 and V0, you can immediately obtain these expressions. So this is a very straightforward way of determining what is the orientation of the pericenter, what is the direction of the pericenter given the initial conditions, okay, and also the other unit vector that we use in the perifocal reference frame. Now here we have used that h, which is the magnitude of the angular momentum, can be expressed in this manner. Okay, so since h is the cross product between r and v at any time, it is true that it is also true at the initial time. So we can write it like this. Okay, so sorry, this is in general, which we will use later, and particularizing this expression at the initial time, we get what you have over there. Okay, so of course this is constant, and that's why we can write this expression at any time. Now, so we already have an expression of I and j in terms of R0 and V0. So if we take the expression for R and V at any later time, okay, so we have the x and y as functions of time, we can insert these expressions for I and j over here. So we can replace them and we will obtain the expression of R and V at any later time expressed in the vector basis of R0 and V0. Okay, so that's basically what you have over here. And here we can identify essentially two terms and their derivatives. So the thing that is multiplying R0, we are just going to call it F, okay? And whatever is multiplying V0, we will call it G. So F and G are the so-called Lagrange coefficients. Okay, you have them here again. And in essence, they are quantities that depend on time, okay, because x and y depend on time. And they also depend on the initial conditions through I0 dot, x0 dot, y0, x0, and also h, which has to be computed from the initial conditions. So these are the Lagrange coefficients, and it is quite straightforward to obtain more general expressions of f and j as a function of theta, for example, by introducing the expressions that you already know for the trajectory. Okay, so if you use this and you also decompose r in terms of x and y, using the expressions of cylindrical coordinates, you eventually can work out the expressions of f and j in terms of theta. Okay, for now it's sufficient to know that these expressions exist. Some interesting aspects of these functions is that if we particularize f and j at t equals 0, we have to match the fact that r is equal to r0 and v is equal to v0 at t equals 0. So that means that the functions have to look like this. Okay, so f0 is 1, j0 is 0, and the derivatives are 0 and 1 respectively. Moreover, since we have to keep the constraint that the angular momentum vector is constant at all times, and in particular the magnitude of this vector is constant at all times, if we compute the cross product of these expressions, we will find that f g dot and f dot g have to satisfy this. Okay, so the difference between these two has to be always equal to 1. So that means that these four values, okay, f, g, f dot, and g dot, one of them is not independent. It depends on the others through this constraint. All right. So perhaps the interesting thing for the rest of this lecture is that this approach is convenient to parameterize the trajectory also in terms of theta. Okay, eventually we can parameterize the trajectory in terms of theta, which is something that we already have. So this is not getting us any closer to parameterizing the position and the velocity as a function of time. And indeed, there is no simple analytical expression for f and g as a function of time. It's just not possible to obtain that. So we have to try to find a different way if we want to do that. A possibility and perhaps naive way of obtaining this time dependence of the position vector would be to expand in series the position vector in its Taylor series, as you can see over here. So this involves the different derivatives and the powers of the time difference from the initial time. So in order to obtain this time series, we have to particularize these derivatives at t0. So the first terms of this series are quite straightforward to obtain. In particular, for n equals 0, we just have the initial position. For n equal 1, we have the first derivative of the position, which is the initial velocity at time equals 0. And the initial acceleration is also something that we can obtain quite easily. So if you take the equation of motion of the body and you particularize it at t0, you obtain this value for the second derivative. All right, and moreover, this equation before you particularize it allows you to obtain any other derivative that you want. Okay, so if you start with the non-particularized expression and you take further derivatives over here in time, you can get the third derivative, the fourth derivative, and so on. So this allows you to write the position vector as this series expansion. So while this would be an approach to obtain the position as a function of time, which would yield an analytic result, although with an infinite number of terms. We can think of truncating this series, right? For example, we can keep, I don't know, 4 terms, 5 terms, and use the resulting expression to estimate the position vector. So actually this works, but unfortunately this does not work very well. It is only a good approximation for very small values of delta t, okay, where delta t is the increment between the initial time and the current time. So this is not a general, a sufficiently good approach in general. So we are going to try to find a different way of finding this relation between the position and time. using geometry. Okay. Observe that it is possible to use this expansion also in the functions f and g that we introduced before. So it's also possible to obtain f and g as a series expansion in time, but we have the same problem. Okay, so we have to truncate the series at some point, and that means that the series is not valid for all values of time, just for small values of delta t. It represents a good approximation. A different and surely better way of obtaining the time position relation is to use the so-called Kepler's equation. So Kepler's equation does not use any time series expansion. Instead, it relies on the geometry of the problem. In order to obtain the Kepler's equation for the elliptic case, we are going to first work out some preliminaries. So if you remember from the last video, we had introduced the auxiliary circle and the angle here that we call the eccentric anomaly, E. So the eccentric anomaly was defined as the angle from the center of the conic to a point B prime, which is a corresponding point to each point on the ellipse, just by taking a vertical. Okay, so the corresponding point to B over here is the point B prime through a vertical line intersecting the auxiliary circle. So that angle is what we call E. We had also provided a number of formulas relating E and theta, but we hadn't demonstrated them. So let us try to work out some of these formulas. In particular, I'm going to start with the first one over here. Before we get there, let me introduce some important concepts that we will use later on. So over here you have the remainder of the trajectory equation and the value of P as a function of A and E. Also the expression for B and the relation between the vertical coordinates of B and B prime. Okay, remember that this relation is given by the ratio A over B. All right. So in order to work out the first expression, I'm going to look into the triangle that you have over there. So let me reproduce it over here to focus our attention better. So this is the center of the conic O. This is the focus. Okay, and this is the angle theta. This is R. This is A. And this is B. And this is B prime. All right. So if we take the cosine of E and multiply by A, this is equivalent to the distance between O to, let's call this point A. Okay, so this is the distance OA. All right. Now, we know, however, what is the distance between O and F. The distance between O and F is the value C of the conic, which we can write as AE as well. So in order to obtain an expression for the distance FA, we can take A cosine E minus AE. All right, so this is the distance FA. But another way of obtaining the distance FA is taking the cosine of theta and multiplying by R. All right, so this is our starting point to reach this formula over here. Now, in order to progress any further, we are going to replace R using the trajectory equation here. So we get something like this. This for the left-hand side, and then for the right-hand side, expanding already P in terms of A and E. Okay, so there we go. We have this expression. Of course, we can cancel A over here. And now we can send this E to the right-hand side and put everything into a single fraction. When we do that, and that's a very easy algebraic step, you will see that eventually you reach the formula that you have over here. Okay, so just from inspecting the figure, it's relatively easy to obtain these expressions. Let us just obtain this other one, and I will let the other two for you to work out. It's just inverting the formulas anyways. If you know the first two, you can obtain the other two. So let me erase over here. So now our concern is not the horizontal distances, but the vertical ones. So the way to do this is to obtain the distance of the segment between A and B. So this is R sine theta, R sine theta, and the distance between A and B prime. So the distance between A and B prime can be expressed as A sine E. Of course, they are not the same distances, but they are basically Y and Y prime. So we know the relation between them, right? So if we take the ratio, this has to be B over A. So again, if we replace R and B with their expressions given here, we work out the expressions a little bit, we can finally write the relation as you see over here. Okay? So the importance of the eccentric anomaly is that it is the most natural variable to obtain Kepler's equation, and we will see that in the next slides. I want to observe something before we move on. That is some special values that happen to find some correspondences between the values of theta and E. So for example, when theta is equal to 0, that is when the object is on the pericenter, okay, both theta and E are equal to 0. So at that particular position in the orbit, the two anomalies, the true anomaly and the eccentric anomaly, correspond with each other. The same happens over here when theta and E are equal to pi, right? When we are at the apocenter. Interestingly, at any point on the first half of the orbit, okay, so between the pericenter and the apocenter, the eccentricity, the eccentric anomaly is smaller than the true anomaly. Imagine, for example, the point over here. So the eccentric anomaly will be all this angle, but sorry, I'm mixing things here. So over here, yeah. So the eccentric anomaly will be all this angle now, while the true anomaly will be all this angle, right? So the true anomaly is larger than the eccentric anomaly in the first half of the orbit. The opposite happens on the lower half, okay? So when we are in this half plane over here, the opposite is true. Theta is smaller than E. So with this, we are ready to obtain Kepler's equation. And our starting point is going to be the area rate equation that we have obtained in previous videos. So remember that from the conservation of angular momentum, it's possible to write down the differential of area swept by the radio vector per instant of time in this manner. So integrating this equation, this differential equation in a full orbit, we obtain the expression for the period, okay, the period tau, which was related with the area of the ellipse, which is pi AB. If we integrate instead between an instant time, which can be, for example, the instant at which the object is at the pericenter, and an arbitrary instant of time t, we obtain the relation between the time difference and the area swept by the radio vector up to that point in time. All right, so basically, if we want to use this expression to get the relation between the position and time, we need to compute this area. All right, so that area for when the body is over here is this area that has been shaded in the drawing. So it's part of the area of the ellipse, and of course it's an area that is difficult to determine right away. So we are going to have some workarounds in order to find it. All right, so first of all, we are not going to get that area directly, but instead we are going to find the area in this small piece. Okay, so using the letters that you have in the drawing, this is P for the pericenter, this is B, and this is C. We are going to call this the PCB area. All right, once we have that, we will have to subtract this A2 triangle, but we will be good to do that later. Okay, so since this is a piece of the ellipse, it's actually easier to find the corresponding area in the auxiliary circle. Remember that the auxiliary circle is your friend for this type of calculations. All right, so instead of computing that directly, we are going to compute this. So this is the PCB prime area. All right, and since this is part of the circle, it's actually easier if we compute the area of this circular sector, for which we have a very simple formula, and we subtract the area of this triangle over here. Okay, so let's call this a 3, for example. All right, so let's focus first on the full circular sector from O to P to B prime, and let's see how we can obtain that. So by definition, the area of a circular sector is the value of the angle, all right, so E, multiplied by the radius squared divided by 2. So that is the area of that circular sector. So if we want just to have this part over here, we need to subtract this triangle. Okay, so let me use a different color. We need to subtract this triangle over here. Lucky for us, the area of the triangle is very straightforward, so we know how much is the base, how much is the height, and we just have to use that. Okay, so actually we have that in terms of the eccentric anomaly, which is what we want. All right, so the area over here, this small piece of the auxiliary circle, is going to be this quantity minus the area of the triangle, which is A cosine E, A sine E divided by 2. All right, so the result of this is the PCB prime area. Now, in order to go from the auxiliary circle to the ellipse, remember that we have the relation between the vertical coordinates. So y prime divided by y is equal to A over B. Right? So when we apply that, we can convert that PCB prime area into the PCB area that we're looking for. And that's basically what you have over here. Okay. So the last step is to subtract the area of this triangle. Let me color it in blue, all right, in dark blue. So how can we get the area of this A2 triangle? Now, again, it happens that it's easier to work in the auxiliary circle. So the vertical distance between C and B prime is the vertical distance that we used before, all right? So that's A sine E, okay? Now, if we multiply that by the scaling factor B over A, then we will get the distance between C and B, which is the vertical height of this triangle, okay? So that's one side. For the other side, for the base of this triangle, we have to consider the distance between O and F, which is something that we already know is the distance C of the ellipse, which is equal to AE. And if we subtract A cosine E from that quantity, we will have this distance, which is what we are looking for. All right. So in summary, we can write the area of that triangle as you can see over here. All right. So the scaling factor has already been applied to the height. That's where this B comes from. And the resulting expression is what you see on the screen. So finally, if we subtract the area of this triangle to the PCB area, then we can find the area swept by the radial vector since the time of passage by the pericenter. That's what we call AT. And here is the final result. So using the expression that we derived initially by taking the ratio between the partial integration and the full integration along one orbit, we can get finally Kepler's equation over here. Right? So that is the result that we were looking for. Observe that this result does not relate directly the true anomaly with time, but instead it relates the eccentric anomaly E with time. And that's why the eccentric anomaly is so useful, because it's the most natural variable to use to solve this problem. Okay. If we now introduce the expression that we have for the period, we can write this expression as you see over here. Now here we have introduced the definition of the mean anomaly, okay, which is another angle variable, but is not actually something physical that you can identify in the motion of your body. This is basically a non-dimensional expression of time. Okay, so this is your dimensionless time variable, and it's just the time multiplied by this mean angular rate in the elliptic case. Okay, so that's your time variable over there expressed in a more compact form. So this equation, the equation of Kepler, finds the relation between E and the time variable, the mean anomaly. And you see that they are basically the same, okay? M is equal to E. The only difference between M and E is this small correction, assuming that E is small, the eccentricity is small, which is a sinusoidal correction due to the eccentricity of the orbit. It's quite instructive to plot the eccentric anomaly E versus the mean anomaly M, okay, or ME. So you see that in essence, when the eccentricity is 0, they are equal. Okay, that's the case for a circle, which is the easiest case. But as you increase the eccentricity, you observe this sinusoidal variation on top of the linear growth of the variable E as a function of M. Okay. Moreover, we can see that E and M are the same at 3 points in this diagram. All right. So this is, of course, the value of 180 degrees, okay, or pi, 0 and 2 pi. Okay, so this is pi. So again, just like what we had between the true anomaly and the eccentric anomaly, which were the same at 0 and pi, the same happens here between the eccentric anomaly and the mean anomaly. Moreover, we see that in this part of the orbit, the upper part of the orbit, E is greater than M, and in this other part, E is smaller than M. All right. To the right, you can see a slightly different diagram. Here we have plotted ME and over here the true anomaly theta. So you see that it follows a similar shape, although the differences are more marked. Okay, you see that as eccentricity increases, you have this oscillation with respect to the black line over here, which is no longer a sinusoidal term. It is something slightly more complicated, of course, because you have to account for the relation between E and theta. Okay. So in summary, what we have found, this Kepler equation allows us to find the relation between time and the eccentric anomaly. If we want the relation between time and the true anomaly, we have to use the expressions that we have to relate E and theta. Okay, so those are analytic expressions that present no problem. Another way to reach this result, the equation of Kepler, is a more analytical one, is by working out with integrals directly. So not relying on the geometry of the ellipse. So in essence, we are going to do the same type of work, but it is disguised in analytical change of variables. So let us go back to our expression of h, which we can write as r squared theta dot. And of course, this allows us to pose this integral. Okay, so in here you have the implicit relation between t and theta. Okay, but if you want to get any further, you need to solve these integrals for any value of t. So the way to do this is to apply a change of variable. And in fact, the variable that we want to change into is the eccentric anomaly, of course. So we start with the formulas that relate theta with E. And in fact, we start over here with the cosine of theta and we take derivatives. Our goal is to find how to replace the differential of theta in terms of the differential of E. All right, so you have the algebra here on the slide. I will skip it for the most part, but you can hopefully follow it without any problems. In essence, I have taken one step of derivation here. All right, so you see already the differentials that I'm referring to, but I want to reduce everything to an expression in terms of E. So I'm going to change this sine of theta using this formula in terms of the eccentric anomaly. All right, so now that we have this, we have the expression that we are looking for. Simplifying some of the terms, eventually we reach this result over here, which is the expression for the differential of theta in terms of the differential of E. Now, if we use the expression for the trajectory in terms of E instead of in terms of theta, you can replace everything in this integral and express it just as a function of E. So the final result is what you have over here. And this is something that can be integrated without any problems now. All right. The final result is what you have here on the right, where this is just the mean anomaly ME, and NE is, of course, the mean angular rate. Okay. So this is another way of reaching this result for the Kepler's equation. Now that we have the Kepler's equation for the elliptic case, let us see what we can do with it. Okay. Well, basically, there is two directions that we want to work with this equation. One possibility is that we know theta, and from theta we can find the value of E, and from E we can then find the value of M, which is the same, of course, as finding the value of T. All right, so one possibility is to work in this direction. This direction poses no trouble, no problem, because going from theta to E is a matter of using an analytic formula, and going from E to ME actually uses Kepler's equation in the easy direction. Okay, so you just input your values here, and you compute ME, and you are done. And once you have ME, which is your non-dimensional time, you have your time. All right. Now, this allows you to build, for example, a table where you have theta, E, and T. So you start with given values of theta, you compute the corresponding values of E, and using Kepler's formula, you compute the corresponding values of T without any problem. Yeah. The difficulty is when you want to solve things in reverse. So when you have time and you want to find the value of theta for that particular instant of time. So that's not an easy problem, because when you have time, you have ME, and solving this equation in reverse is actually very difficult. Okay, it cannot be solved by hand. You need some sort of numerical solver in order to do the job. Okay, so in order to do this, we split the problem into parts. Okay, so given T, we can compute ME, no problem. So now the difficulty is going in this direction, from ME to E. All right, so that's the first part. Once we have E, we can continue and get theta without no difficulties, because we have the formulas for that. So how can we get E from ME? One possibility is to use a solver, okay, such as Newton-Raphson solver, to iteratively compute the value of E with any chosen level of accuracy that we want. All right. So we first write our Kepler's equation in this form. This is what we call the error function. Okay, so if we find the solution for E, clearly this function has to be equal to 0. If we try this function for different values of E, the result will not be equal to 0. Okay, so we want to find the value of E that makes this function to be equal to 0, where M is a fixed value given by the time that we are solving for. So the way to proceed is as follows. We can take an initial guess for our problem. Okay, so we can imagine what is the possible value of E, or more or less where E should be. And if we don't have any better choice, we can perhaps just use the value of the mean anomaly at that instant. Okay, if the centricity is small, clearly the difference between E and M will be only due to this small term, so it should be close enough to the solution that we are looking for. So now that we have this initial guess, unless we are terribly lucky, this will not be the solution for the problem. So we can compute the value of the error committed for that guess. Right? So we just enter in the F formula, and we compute the value of F0, which is the error associated to the initial guess, E0 of the problem. So now that we have this error, we can linearize the error equation. All right. So our error equation can be expressed as follows: F0 plus F prime evaluated at 0, E minus E0. Okay. So of course there is higher order terms, but if you just keep the linear terms in this expansion, you have the equation for a straight line. And in this straight line, you can solve for the value of E that would cancel the error if the problem was linear, which is not. Okay, so inverting that relation will give you a hopefully better guess of the solution. Let's call that guess E1. Okay, this has been inverted over here. So this is the iteration formula that we use in the Newton-Raphson's method. In essence, we have the error at that initial guess and the value of the derivative at that initial guess. And this allows us to compute what should be the expected correction we have to use to modify the initial guess to get a better guess. All right. So what is the derivative? Well, the derivative is written over here. No problem. There is simple enough to compute. So this will not give us the solution either, but hopefully if we are sufficiently close to the solution, the new guess will be better than the previous one. And we can iterate this procedure until we get a match of the solution as good enough as we want. How can we define what is good enough? Well, we can compute what is the absolute value of our error in the nth iteration of the process. And we can also check what is the variation of E between the new guess and the previous one. Okay, we can normalize it with this if we want. If these two variations, if the error and the variation from the previous guess are smaller than a given tolerance that we can choose a priori, which can be arbitrarily small, then we conclude that, okay, we have the solution with the accuracy that we are looking for, so we can stop the iteration and declare that this guess that we have right now is the solution that we want. All right. To visually understand what's going on, basically, imagine that this is the error function, okay, that we are going to try and solve. Okay, so this is FE, this is E, and this is FE. Okay, so imagine that we start with an initial guess over here. So this is the value of E0, and this is the value of F0. The linearization that we are doing here allows us to find this straight line. So this straight line is a local approximation of the function, but it's not the function. And since we are using this approximation to find the new guess, okay, we are trying to cancel not the function but the approximation. This is where E1 will be located. So you see that it's already closer to the true root of this function. Yeah. So we can continue the procedure. We can compute the error here, compute the line that goes through that point, and then we will get E2, and so on and so on and so on. And you see that just in a few iterations you can get very, very close to the actual solution of that problem. Okay. Again, the reason that we have to use this is because we cannot invert this equation directly. Okay, this is a transcendental equation, and that's why it's not possible to do it by hand. So this is one of the best ways that exists to find the solution of this equation when working in this direction, from time to eccentric anomaly. All right, so let us take a look at how all this works with an example. In any case, we are going to implement the solver in the problem sessions of this week, so you can actually get more practice and more insight on how to do this on your own. So let us imagine that we want to solve Kepler's equation in the difficult direction. So we have the non-dimensional time here expressed in degrees, and we want to compute the eccentric anomaly. So we assume that, of course, afterwards, if we want the true anomaly, we can use the formulas and so on. So let us recover here the equation for Kepler's. Yeah, that's the one. So one first important thing to notice is that even if the initial data is given in degrees, we need to apply everything in radians. Okay. And the reason for this is that, well, you have angles that are not inside any trigonometric function over here. So the only way that this works out is if everything is expressed in radians. So let us write the compact version of the iteration formula for the Newton-Raphson method. So here you have the error function. Okay, so it's basically Kepler's equation with everything sent to the right-hand side. And here you have the derivative of that function. Okay, and both of them have been evaluated at the guess number n. So once you have the nth guess of your problem, you can get the n plus 1 guess by applying the iteration formula that you have here in this very compact form. So to start with n equals 0, we are going to take as our guess the value of the mean anomaly. Okay, in the absence of a better choice, this is probably a good way to start, assuming that the two angles are not going to be very far from each other. And for our tolerance, epsilon, we are going to take 10 to the power minus 8, both for the absolute error of the function and for the relative error of the relative variation of the eccentric anomaly between iterations. All right. So this is something that, as I was saying, you will implement on your own, but here you can see how it works out. Okay, so in essence, we apply iteration after iteration, and even if I'm doing the computation in radians, I have expressed everything back in degrees for simplicity in order to be able to better visualize what's going on. All right, so for our initial guess, the error is quite large. Okay, so we have something in the order of 0.3. Okay, 3 times 10 to the minus 1, and so the error is quite large. It's clearly larger than our expected tolerance, so clearly this is not a good enough solution. This is just the initial guess, and this is the error that we will have after moving the iteration once. Okay, so this is the delta E between iteration 1 and iteration 0. You see that it's also a relatively large value. Now, as we use the iteration formula to find the value of E1, you see that it has already changed quite a lot, from 235 to 220 degrees. Yeah. Now the error is already smaller. You see that the error has gone down in 1 order of magnitude. And similarly, this one has also decreased. Okay. Continuing to iterate will change the value a little bit. Okay, so you see that here it has recovered a little bit the value up. Okay, so from here to here it decreased, from here to here it increased. It doesn't matter. It depends on the particular point where you are iterating, so that can happen. But what really matters is that the error here has already gone down by a lot. Okay, so this is almost 10 to the 5 to the minus 5 because this is a 9. But in any case, this is a big improvement over the error that we had before, and the same happens over here. And in just one additional iteration, we achieve our desired tolerance. Okay, you see that the value of the angle doesn't seem to change over here because we are just keeping 3 significant figures, but in any case, the error is clearly much smaller. And perhaps you can notice something interesting in this trend. Every time that you take an iteration, except perhaps initially where things behave a little bit different, when you are sufficiently close to the final solution, the error on each iteration doubles the order, the exponent here. Okay, so we go from -6 to -12. So this is what we know as second order convergence, and this is a characteristic of the Newton-Raphson solver when we have a simple root in the function that we are trying to solve. Okay, so this is really a very good property. This means that in just a very few iterations, here just 3-4 iterations, we can actually reach the accuracy that we want very quickly. Before we close the elliptic case, I want to tell you about the problems that exist when the eccentricity of the orbit is very large. Okay, so here we are concerned about cases which are still elliptic, okay, which have an eccentricity smaller than 1, but quite close to 1. All right. The problem is that in those cases, the relation between E and M is not so well conditioned. In other words, if we have our Kepler's equation here again, sine of E. Yeah, the relation when E is very large actually becomes bad conditioned, ill conditioned in parts of the orbit. And this is related with the fact that the time variation of the position of the body in the orbit changes very differently when we are near the pericenter and the apocenter. All right, so if you look at the drawing here on the right, This is the central body, okay, the primary body of the two-body problem, and the black dots represent the position of a satellite at fixed intervals of time, right? So you see that our satellite goes around the central body very quickly near the pericenter. Okay, there are just a very few points over there, and spends most of the time in this part of the orbit close to the apocenter. All right, the fact that this happens near values of the true anomaly equal to 0, which correspond with values of the eccentric anomaly near 0 as well, means that near these values the the relation with time is ill-conditioned. In other words, small variations of E in Kepler's equation around these positions will mean huge variations of M, right? So inverting the problem represents some numerical difficulties. If we plot, in fact, M versus E, you can see that for very large values of E, the function becomes almost flat in this region. Okay, so that is related with this difficulty of inverting the relation. So it's something that we have to take into account. This may mean that in those cases we have to take a better initial guess for the eccentric anomaly when applying the Newton-Raphson method. And in actuality, what people do in numerical codes is to use other variables and other schemes to solve the problem than these ones when we are close to these high eccentric orbits. Okay. All right, so let's move on to the hyperbolic case. We're going to reserve the parabolic case to the last one as it goes a little bit differently. In the case of the hyperbola, we can find a relation similar to the ellipse for Kepler's equation using the so-called hyperbolic sine and hyperbolic cosine functions rather than the standard trigonometric sine and cosine. So to get there, let us first observe that the Kepler's equation for the elliptic case is not valid in this form for the hyperbolic case because the left-hand side has an imaginary number. Since the semi-major axis is negative in the hyperbolic case, we should better write it explicitly as an imaginary number like this. Okay, so if we multiply this equation through by I, we can rewrite it in this other form. So you see that a real E value doesn't make sense in this formula. We need an imaginary E value. So it actually makes sense to introduce a new symbol for I times E, which we will call H. All right, and in fact we will refer to it as the hyperbolic anomaly. All right, so by doing this change of variables, we will recover an equation that is real with all the variables real, and it will be sufficiently good to solve the time problem in the hyperbolic case. So observe that, as you can see here on the right, on this reminder of the trigonometric and hyperbolic function formulas, if you have a sine and the value of the argument of the sine is an imaginary number, well, when you write it in terms of exponentials, the exponent in those exponentials is going to become a real number. So there will be a relation between the sine and the hyperbolic sine, and in fact this is the relation that I have presented over here. Right, when we have the sine of I times a real number, we can write that as I times the hyperbolic sine of the real number. And similar formula for the hyperbolic cosine and the cosine is the one that you see over here. So when we replace this E in here with I times H, okay, we can replace that by I times the hyperbolic sine of H. And with this minus I over here, that becomes a plus. So finally we get this formula where you see that everything is indeed real with all the variables real. So this is what allows us to solve the time problem in the hyperbolic case. This hyperbolic anomaly is something a little bit more complex to visualize than the eccentric anomaly in the elliptic case, but it plays the same role. You can think of this as a change of variable, the most natural change of variable that allows us to integrate the the time law. And in fact, there are still formulas that allow you to relate h with theta. All right, those formulas are identical to the ones that we had for to relate the centric anomaly with the true anomaly in the case of the ellipse. We just have to adapt them by doing E equals I times H. Okay, so if we do that, we recover the necessary formulas for the hyperbolic case. Finally, in analogy with the elliptic case, we are also going to define two quantities, which are perhaps less meaningful in the hyperbolic case because it is not a closed orbit, but an open trajectory. But nonetheless, we still refer to them by those names. So we are going to call the mean angular rate in the hyperbolic case as this square root, okay, with already the minus inside it. So this is a real quantity. And also the mean anomaly in the hyperbolic case, which is in this case our non-dimensional time, right? So just as we did with the elliptic case, we can call all of these single non-dimensional time variable, and that will be our MH. Okay, so in order to give you basic understanding of what is this hyperbolic anomaly that we have introduced, observe that first of all, it is the natural change of variable that allows us to integrate the time equation. Okay, so similarly to what we did in the elliptic case, we can proceed analytically with the integral and work out with the change of variables. And that's basically what comes out in the hyperbolic case as well. So in essence, here, not all the expressions are shown. What we have to do is to find an expression for the differential of theta in terms of the differential of h. So one would take the expression of the cosine of theta in terms of the hyperbolic anomaly, take derivatives there, and eventually one can find this change of variable. So once we have that, it is possible to integrate it, and the final result is the Kepler's equation in the hyperbolic case, which we obtained before. Now, geometrically, it is possible to find what this hyperbolic anomaly means, or at least to have a general idea of it. So basically, let's go back to the elliptic case, and let us write the eccentric anomaly in terms of the area, the shaded area that you see in white. Okay, so using the expression of the area of a circular sector, it is possible to write E as 2 times the area of that circular sector divided by a square. Okay, well, in the case of the ellipse, we had, lucky for us, the auxiliary circle. For every point in the ellipse, we could find a point in the auxiliary circle. In the hyperbolic case, it's not so easy, but we can define something similar. We can define an auxiliary equilateral hyperbola. All right, and when we do that, it is possible to find the hyperbolic anomaly in terms of an area, just as we have done over here for the case of the ellipse. So imagine this is the trajectory, the hyperbolic trajectory that we have. We define the auxiliary hyperbola with the same a, but with an eccentricity of a square root of 2. So this is the auxiliary equilateral hyperbola that we have introduced. Okay, they both have the same center and the same pericenter. So for every point on the original hyperbola, there is a corresponding point on the auxiliary hyperbola that can be found through a vertical, just as in the case of the ellipse. Okay. Now we can find the value of this area, all right, and the hyperbolic anomaly will be defined in terms of this, just with a formula the same as before. Okay, so you see that there is at least some symmetry in terms of the eccentricities, the centric anomaly and the hyperbolic anomaly in the elliptic and the hyperbolic case in terms of this area. Of course, for our day-to-day work in this course, we don't really need to remember that there is this geometric interpretation of the hyperbolic anomaly. It's just we can think of it as the variable, the change of variable that allows us to solve the time problem, and we don't actually need to give it this interpretation. We can just use this equation to solve the time relation, and that's it. The last case is the parabolic case. Now remember that the parabola is just the boundary case between the ellipse and the hyperbola, and in reality it's very difficult to to accomplish a true parabola. Actually, having the eccentricity really equal to 1 is almost impossible. In any case, unlucky for us, it's very easy to integrate directly the equation for the time dependence, okay, since our trajectory now with eccentricity equal to 1 looks like this. All right, so working with the trigonometry, it is possible to rewrite the denominator of this expression as you can see over here. And that means that we can integrate right away the expression. This is the final result after integration, right? So this allows us to solve directly between MP and theta, okay? And the same as before, it actually may require some solving if depending on the direction that you are going. In analogy with the previous cases, we can label the tangent of theta half as P, okay, and call that the parabolic anomaly. In that case, this formula becomes this. Okay. Now, also we can call the square root of mu over p cube the parabolic anomaly. All right. Again, it doesn't represent anything physical, but it's just to keep the analogy with the other cases as well. So you see that in this case we have this different formula for Kepler's equation, but it's possible to solve it nonetheless, of course. In this final slide, you can see some of the formulas taken from the Vallado's book, which is one of the classical references for astrodynamics. Here you can see the formulas for ellipses, parabolas, and hyperbolas that relate the different anomalies. Okay, there is a slightly different notation that is being used. So here, nu is used instead of theta, and v is used instead of p. But otherwise, everything else remains the same. So this allows you to have a quick reminder of all the formulas that allow you to go back and forth between the different anomalies. To conclude this lecture, let us just talk a little bit about the so-called universal formulation. You see, we have solved separately the elliptic, parabolic, and a hyperbolic case. In each case, we are using a different change of variable to integrate the time equation. So we have a different anomaly that we have to use for each of the cases. This is all right, but it makes the logic of solving the problem in the general case more complicated. Imagine that you have to put this into a numerical code. You would have to use different switch cases to separate the three situations. And in fact, it is actually a little bit tricky to work with cases that are parabolic or near parabolic, because you have to decide where to do the transition between one formulation and the other. So in all cases, you basically have a Kepler's equation like form, which you can solve. In one direction is always very easy and you can solve it directly. In the other direction, from the time to the anomaly direction, you have to use some type of solver, which can be the Newton-Raphson solver, as we have seen in the slides about the elliptic case. The same thing can be done for the other cases as well. Now, the universal formulation is a different approach where we try to cover the three cases simultaneously. So we don't have to have a separate formulation for each of them. This is done by using universal variables, and I just wanted to point out that they exist. You can have a little bit more information about this in the lecture notes, but specifically, if you're interested in this topic, you should go to see the references that I point over here. The universal formulation has also some advantages. For example, dealing with the problem for high eccentricity elliptic orbits, where the variation near the pericenter is faster, and so on. And it's actually quite convenient for numerical codes. Unfortunately, of course, those universal variables, that universal anomaly that we use in this case, is far more complicated and far more abstract than any of the anomalies that we have introduced in this video. All right, that's why we are not going to go deeper into that case. Suffice to know for you that this formulation exists and where to find it in case you need it. All right, so with this we finish with the two-body problem. What we have seen here is, however, very important for the rest of the course, as it sets the basis for many of the things that we will do in the coming weeks. In the next video, we will begin with the study of orbital maneuvers. Thank you and see you next time.